So, today we are going to discuss influence of machine and process parameters. Also, we will see the effect of fiber parameters as well. So, basically it is fiber, process and machine parameters on the quality of the yarn, or how the yarn properties are affected by these parameters or variables, whatever we say. So, basically influencing parameters are fiber, machine and process. So, we try to produce fiber, we try to basically process fibers of different types, or we can change the fineness or length or cross section, different types of fibers we can process with different dimensions. So, if we go further details into these parameters, then you see fiber parameters simple are length, the blend, in the case of we go for blend ratio, length is just not once, but we can also add fineness along with length. The machine parameters are, in this case, are one is nozzle pressure, nozzle angle and spindle diameter. The nozzle pressure is, we can say, is more related to the process, whereas the nozzle angle and spindle diameters are basically part of the machine parameters in this case. The process parameters are, one is the delivery speed, that is the production speed. The other thing could be the count of the yarn and the distance between the front roller nip and the nozzle. So, these three types of parameters that we have listed here, they can be further classified. So, fiber parameters, it could be length, it could be fineness, or it could be the proportion of two fibers when they are blended together and processed. And the machine parameters are nozzle angle, spindle diameter, nozzle pressure, also we have listed here under machine, it could be a part of process as well. The process parameters are basically delivery speeds, the count of the yarn that we are going to process and the distance from the front roller nip to the nozzle mouth or entry to the nozzle. So, these are the parameters, and all these parameters have some effect on the processability of the fibers and also on the property of the yarn. So, first we will discuss the influence of fiber parameters. Generally, with increase in fiber length, the wrapping is going to be better. The more fiber length will be available, better will be the wrapping, because the wrapping length availability also will increase, and hence wrapping is going to be better. Like if we compare between comb sliver yarn and carded sliver yarn, we all know that in the carded sliver we have a lot of short fibers present. When we go for comb sliver, short fibers have been eliminated. That means there is a change in fiber length. Not only that, there is an elimination of short fibers as well, and it has been shown that a yarn made from comb sliver will also have less hairiness and they will also be better in terms of evenness of the yarn. The yarn will be much more regular. At the same time, the yarn is also going to be little stronger, because in the combed fiber we have most of the fibers are long and they can better wrap the core part of the yarn. So, since longer fibers will be more in number now, so they can wrap better, and as a result the yarn will be stronger. The uniformity is better mainly because of the evenness, that is the drafting system will be able to process the fibers much better because the short fibers are not there. And the fiber loss that happens during spinning operations, that fiber loss is going to be less because short fibers are not there in the case of combed yarn or combed sliver when you fed. So, there is always an advantage in having the combed sliver for cotton. At the same time, the additional advantage will be that in combed sliver the dust particle also going to be less, the trash particles also going to be less. So, they will also have effect on the processability. So, they have an advantage that processability also will be better if we go for combed sliver as a feed material in comparison to carded sliver. In the case of polyester cotton blended yarn, it has been shown that higher proportion of cotton will make the yarn less even and will also have higher number of imperfections in the yarn. So, more cotton means a inferior quality yarn that will be produced, because cotton will contain some short fibers. Even if it is combed, there will be some short fibers still left, because through combing we may not be able to remove all the short fibers which are present in the sliver. Some short fibers are still left, and therefore, if we have more percentage of cotton in polyester cotton blend, relatively the yarn will be inferior in comparison to when we increase the percentage of polyester in the blend. The other important thing is already stated here, the short fibers content decreases. As they decrease, yarn becomes more even and thin places and naps also decrease. So, this is all in the context of cotton or a blend which contains cotton. So, it could be cotton polyester blend, it could be cotton viscose blend, it could be cotton modal blend. So, any blend that contains cotton and the other fiber, which could be any either synthetic fibers or regenerated cellulosic fibers. We remember that cotton basically means short fibers are there, dust is there, some trash is there, and therefore, presence of cotton will always make the yarn a little more uneven, and there is a chance that thin places also can increase, and but so therefore, the reverse is true if the proportion of cotton is less. Then when we come to blend, in cotton polyester blend there is no apparent tendency of the cotton or the polyester fibers to become either wrapper or core fibers. That means, if the sliver has cotton and polyester both and they are intimately mixed, then each fiber has equal probability to make wrapper or becomes a part of core. The probability of becoming a wrapper or becoming a core is same for both polyester and cotton fiber. The other thing is, yarn with higher proportion of cotton fiber are more uneven, as we have already discussed. In any blend, if the cotton percentage increases, the yarn becomes more uneven. It becomes more hairy and have higher number of imperfections and thin places. This is what happens when we go for blend where cotton is there. We can also have 100% polyester yarn, 100% viscose yarn on vortex spinning system, or we can have a polyester viscose blend where cotton does not exist. But when cotton is there, though many times we need a blend where cotton is required, but with cotton we have to remember that more the percentage of cotton, the yarn is going to be uneven, little hairy, and there may be higher number of imperfections and thin places. Like it has been shown that in a cotton tensile blend, higher percentage of tensile can increase yarn tenacity. That means tensile is a stronger fiber than cotton. So, if we add more tensile, the strength of the yarn is going to increase. Now, we go to the one of the most important parameters, that is nozzle pressure. So, if the pressure is increased, the velocity of the air which is entering the nozzle is also going to increase. Typically, air pressure ranges between 4 kg force per centimeter square to 6 kg force per centimeter square. So, increase in nozzle pressure will increase the axial, radial and tangential air velocities inside the nozzle block. Now, increase in radial velocity is going to have an expanding effect of the fiber bundle that will result in more open trail ends of the fibers. See, some fibers, as we have already discussed, that whatever fibers are flowing from the front roller nip to the nozzle, and first they enter the nozzle entry point and then they move towards the tip of the spindle. Now, when they reach the tip of the spindle, some of the fibers will be detached, especially the trailing end of some of the fibers. The leading end will be a part of the core always, but some trailing ends will be detached, and this detachment process is because of the sudden expansion effect that is there, because this radial velocity component that is going to expand. So, they are going to, that means it is going to separate the fibers from the bundle, and therefore, the fibers which are lying at the periphery of the bundle, they are likely to be separated from the rest. So, the trailing end which are lying at the periphery of the bundle, they are going to be separated. The leading end of those fibers may still be a part of the yarn core. So, the separation also is due to the flow of air through the hollow part of the spindle, and therefore, when the nozzle pressure is high, expanding effect is going to increase in the twisting zone which is here, and we expect more fibers to get detached from the main bundle and form wraps. So, wrapper fiber we would expect to increase if we go for higher nozzle pressure. Increase in tangential velocity causes an increase in the mean angular velocity of the free ends of the fibers. See, the fiber ends, the trailing fiber ends will hang and will actually roll over the spindle top, or say that is what is called swirling action, which we have discussed in the previous class. So, that swirling speed is going to increase if we go for higher nozzle pressures. So, that means the trailing end which are detached and now they are swirling, and they will swirl at a very high speed, and when they are swirling here in this zone, that is here or here, there is a chance that there will be lot of friction that will develop between the fiber, and because it is in contact with the surface of the spindle, and it may also come into contact with the inner wall of the nozzle block. So, that will be tension also could be quite high. Now, the angular velocity, if it increases, the swirling speed increase basically means there will be more wrapping intensity and tightness of the wraps are going to increase, because the fiber end which is now swirling at a higher speed, it will develop more centrifugal force and more tension on the ends, and they will finally get wrapped around the core of the yarn, and they will be quite tight in nature. So, tightness is going to increase, and wrapping intensity or wrapping density, whatever we say, or frequency of wraps is also going to increase. That is the advantage we get from going from 4 towards the higher side. So, as a result of this, one can expect yarns to be stronger, less hairy, and yarn lean, because if I have tight wrappings, yarn diameter is going to decrease. So, yarn will be lean. Then because wrappings are there, the hairs will not be able to project out. So, it will be less hairy, and because the wrappings are tight, as it is shown here, these wrappings are there, the yarn is going to be stronger. So, we can expect the yarn to be stronger, less hairy, and more compact if we go from lower nozzle pressure towards the higher nozzle pressures. And if we have a tight wraps, automatically it means flexural rigidity will going to increase, the yarn will be difficult to bend. The wrappers, these are the wrappers fiber, these wrappers are going to tightly hold the core, and therefore, the relative movement between the fibers within the core is going to be difficult when you try to bend the yarn. So, yarn is going to be quite rigid in nature. It is the flexural rigidity is difficult to bend in comparison to other yarns. But with nozzle pressure increase, yarn evenness may deteriorate. Number of thin place, thick place naps may increase because of increase in fiber loss at high nozzle pressure. This is also you have to remember that loss of fibers are going to increase now at a higher nozzle pressures, and if the loss is there is a chance that more thin places will be developing, and with the higher pressures there will be more thick place and naps, because the loose fibers which will be moving out, they may suddenly accumulate somewhere, and they will be may become a part of the yarn also. So, actually the yarn becomes more imperfect in a way. Thin place may increase, thick place may increase, naps also might increase, though the yarn at the same time may be stronger now. So, that has to be some amount of, now we have to find out where is the optimum, and if the nozzle pressure is too high, then the trailing end of the fibers, they rotate, and it goes beyond the critical angular velocity. Critical angular velocity is the velocity or rotational speed beyond which some of the fibers will be plucked out from the core. The trailing ends which are rotating violently now at a very high speed, the tension will develop so much that the leading end will move out from the core of the yarn. So, they will be basically pulled out of the yarn core, causing fiber loss, thin place, irregular wrapping, wild wraps, everything will be there if we go for very high speed, very high, sorry, it's not speed, very high nozzle pressure. That means that has to be an optimum nozzle pressure, not too low, not too high will be bad, too low also will be bad. So, you have to find out an optimum. The optimum will depend upon the count of yarn we are going to produce, and will also depend upon the length of fibers that we are going to process. And because of this, at very high pressure the yarn tenacity may even decrease because of this irregular wraps. Wrappings are not going to be very regular, they will be haphazard in nature. So, wraps are the source of strength, that we should remember. So, what we need is basically regular wrapping or uniform wrapping and tight wrapping, and the sections of the yarn, the sections which are devoid of any wrapping fiber, they should be minimum, because any section which is not having wrapping fibers is a source of weak place in the yarn. So, that is also we have to see. So, very high nozzle pressure therefore may not be working in favor of the quality of the yarn. Now, nozzle angle. See here the diagram is shown here. The nozzle block inlet, and this is the spindle, hollow spindle, and these are the nozzles. There will be 4 nozzles and they are placed at an angle. This angle typically is 65 degree or 75 degree or maybe some other value, but typically these are the angles. The changes in nozzle angles results in variations in tangential, axial and radial velocities of the airflow inside the nozzle block. Now, radial velocity we know it is going to expand the fibers, bundle is going to be little expanded, that is the benefit of this. And tangential velocities are going to increase the twisting rate or the swirling rate in this case. So, at high nozzle angles leads to higher tangential velocity and in turn higher twist. This twist basically means wrapping twist. However, it has no effect on yarn tensile properties. That has been stated by some people that though even if it is wrapping more, but still the tenacity has not been seen to increase much. Maybe the angles 65, 75 degree are probably the optimum value of the angles. So, if we want to study the effect of nozzle angles, unless we go for very extreme values, we will not really know that if we what happens at those extreme values of the nozzle angle. So, maybe if we go for 45 degree or 30 degree, 75, if we go 85, 90, maybe there will be difference will be seen, but somewhere in this range probably it is close to optimum, and therefore, even though there are some changes in the wrapping, the tenacity was found not to change much. Now, spindle diameter. So, this is the spindle. So, this is the spindle diameter is shown here, this diameter of the spindle. This is hardly 1.2 mm or 1.3 mm, 1.4 mm, and within this diameter also there is a hole. Through those holes the fibers are passing. So, you can imagine that how how small these holes are. A smaller spindle diameter gives less freedom to the fiber bundle to expand as it enters the spindle. These generate higher friction between fiber and leads to tighter wrappings. Expansions will be less, wrappings are going to be tighter, the fibers are going to be more compact. And with spindle of larger diameter, it will be just opposite of that. Fiber bundle will have more freedom to move inside the spindle, therefore, some twist is lost and wrapping becomes loose. So, smaller diameter means tighter wrappings or compact yarn, whereas larger diameter means little bit of more voluminous type of yarn, and wrapping also can be looser, it is not tight, become looser. Therefore, the yarn becomes bulky and more hairy in the case of larger diameter spindle, but the diameters are actually 1.2 to 1.4 millimeter. This is the range in which the diameter of the spindle top lies. So, that some whatever research has been done, these are the observations that has been made. We come to yarn delivery speed. So, within the nozzle, some fibers are trying to wrap the yarn core, and at the same time the yarn is moving forward. We are trying to pull the yarn out from the twisting chamber or nozzle chamber. So, that is what the delivery speed are. So, the yarn simply, but very, if we try to understand, if the trailing end that is swirling and actually wrapping, getting wrapped, you can say. So, if this is the suppose this is the bunch of fibers which is representing the core moving in these directions, and some fibers ends are rotating, they are hanging like this, and this is rotating. So, if the rotational speed of these fibers are not going to change, because we are not changing the nozzle speed, nozzle pressure, then for the same rotation, if I pull the yarn at a faster rate, the wrapping angle is going to change. That means, the wrapping intensity will change. Higher the delivery speed, wrapping intensity will be less, and opposite will be true if the delivery speed is reduced. That means, the other thing is delivery speed determines the residence time of fibers in the yarn formation zone. How long a fiber is going to stay in the yarn, in the twisting zone, or how long the core is going to stay in the twisting zone. Everything will depend upon the speed with which I am delivering or I am taking the fibers out of the twisting chamber. If other parameters remain constant, a higher delivery speed will mean a decrease in wrapping angle. This will be obvious, because the speeds of this hanging ends are not changing, because that is decided by the nozzle pressure. And if I take this thing out, the yarn moves at a higher velocity, the wrapping angle is going to be less. Like twist in a ring spun yarn is the ratio of rotational speed of the yarn and the yarn delivery rate. Similarly, the wrapping twist in this case will depend upon, will be the ratio of the rotational speed of the trailing end of the fibers divided by the yarn delivery rate. So, there is simple the analogy is there. There the yarn itself is rotating because the traveler is rotating. So, the ratio of these two, that is, when I take a unit length of yarn out, how many turns the yarn rotates, that decides the level of twist. Here, when I take a unit length of yarn out, how many times the trailing end of these wrapping fibers are rotating, that will decide the wrapping twist, or that will decide the, in a way, wrapping angle. Twist, so we can say from twist to twist angle. So, higher delivery speed means decrease in wrapping angle, and increase in irregular wrapping, unwrapped sections and wild fiber generations. The speeds are very high. A reduction in tighter or regular wrapping and long wrappings, decrease in number of wrappings. So, everything goes on the wrong side. Wrapping quality suffers when the speeds are very high. When the speeds are very high, basically means in this case vortex spinning, a speed of 300 meters per minute will consider to be low speed, whereas a speed of 450 or 500 meters per minute will be considered to be a higher speed. So, when we work at the speed of maybe 300 or 320 or 350 rpm or delivery meters per minute, the yarn will be quite good. But as we go from the higher side, in order to increase the productivity, there is a chance that the yarn quality will suffer because of the problem listed here, because the quality of wrapping is going to change, because the residence time of the fiber is too short now. Yarn evenness deteriorates and the number of thin and thick places is going to increase. See, the yarn evenness, that means the drafting speed also has to increase when I am trying to increase the delivery speed. That is the speed of take up roller. I have to feed the fibers also at a very faster rate using the drafting systems. So, there at very high speed, as a deterioration in the drafting of the fibers may also suffer. Smooth drafting of the fibers is going to be affected at a very, very high speed. The other thing is that because the residence time is also very poor or very low, therefore, the yarn as a whole is going to suffer in terms of that thin places is going to be more, and thick places also can increase, because maybe a lot of drafting wave is going to be generated at very, very high speed. The control of fiber in the drafting zone of the rotors, the upon drafting system may not be so good when we go for very high drafting speeds. So, if the control that we exercise on the fibers as they move through the drafting system as well as the twisting assembly, if that control is poor, then lot of faults will be seen in the yarn. So, faults in the yarn is a reflection that the control that we exercise on the movement of fibers is not really good. So, there is an optimum delivery speed with regard to yarn quality, and it depends mostly on the yarn count. For finer count, the optimal speed will be always lower. Finer count basically means we will be going for this case number of fibers in the cross section of the yarn is going to be less, and therefore, the fibers that may choose also may be little finer, and hence the speed needs to be reduced, so that we can get quality wrapping around the core. The other important parameter is the distance between the front roller nip and the spindle. It is shown in this diagram that this is the distance. Front roller nip and the spindle tip is here. This distance is typically could be 19 to 21 millimeters. So, shorter the distance means it increases core fiber length. Part of the fiber, that is, all the fibers are not forming wrappers. Some fibers are, or the entire fiber length itself is in the core, but fibers which are forming wrappers, part of it is in the core, the rest of it is on the surface of the yarn. So, short distance mean increases the core fiber length, leads to better fiber control from here to there. See, from here to there, this length, we have what control we have on the fiber movement. The fibers are very fine, they are fine, they are very fine, and they can be easily disturbed by the movement of the air. They are so fine. So, when it comes from front roller nip, they are released and they come to the spindle tip. The guidance is given because we have a spiral path, and then we have a needle. They are giving some kind of guidance to the fibers, so that they remain to some extent under control. So, if the length is short, then the control will be better. If the length is long, then control will be less. When both the ends of the fibers are tightly assembled, resulting in fewer fibers with open trailing ends, and it will lead to less fiber loss. From here to there, so if the for many fibers, see, this is the nip point and this is the spindle tip. From here, suppose there is a fiber going like this. This is the nip, this is the spindle. So, when both the ends of the fibers are gripped, and this length, let us say, is, suppose the fiber length is, let us say 38 mm, and this length is 20. So, for quite some time, the fiber, as the fiber is traveling in these directions, initially when the fiber is approaching, the leading end is not under grip of the, is yet to reach the spindle. A time will come when it will reach the spindle. Now, one end is gripped by the spindle because they are actually within the bundle of fibers which are there. The other end is gripped at the nip point. So, when both the ends are gripped and they are moving also in the forward directions, in that case these fibers are well guided and they are not going to really get detached from the main body of fibers, and hence they will be mostly part of the core, or when the trailing end is released from the nip, maybe depending upon the location in the fiber bundle. If they happen to be on the periphery of the bundle, they might get detached, but if they remain within the, suppose these are the bundle cross sections and you have many fibers. If a fiber happens to be in the periphery, chances of it getting detached and then forming wraps is going to be more, but the same fiber happens to be in the core part, the central part of the bundle, as the entire bundle is moving forward, then chances that it will remain in the core is going to be very high. So, all depends upon the location of that fiber with respect to the bundle of fibers which are moving together. from nip point to the spindle tip. So, longer the fibers, since most of the fibers will be simultaneously gripped by the front roller nip and by the spindle tip, they are not going to be lost. Fibers which are shorter, or if I increase this distance 20, then chances are that many fibers will be maybe lost. Thus, one expect that there will be less fiber waste, increase in core fibers held with few wrapper fibers. So, when the distance is short from this distance, then we can expect less waste of fibers in the spinning zone, and there will be increase in core fiber percentage held with fewer wrapper fibers. So, shorter distance has a beneficial effect. And if we go to the other extreme, that is the longer distance, fiber length embodied in the vortex span yarn tail will decrease. Critical angular velocity of the fiber with open trailing end is going to also decrease. The leading ends of the fibers are more easily pulled out from the yarn tail, which results in increase in fiber loss and thin place in the yarn. As I said, that these are the hanging fibers now. So, if the distance is more, then the fiber length that is embodied in the vortex span yarn tail is going to see every fiber which are forming wrappers. If these are the fibers in the core and I have wrappers. So, part of the wrapper, every wrapper fiber which is hanging here, part of it is inside and the rest is hanging, and they are then swirling around the spindle or around the, you can say, the main bundle of fibers. So, the fiber length embodied into the vortex span yarn tail decreases. So, this length from here to there, if this is the fiber tail, and this length is going to decrease if I increase the gap between the front roller nip and spindle tip, and therefore, a longer length is going to hang. When the longer length is going to hang, means for the same rotational speed, if the longer length of the fiber is hanging, it is swirling around, the centrifugal force is going to be more on them, and they are likely to be going beyond the critical angular velocity. What does critical angular velocity means? I have already discussed. That means it is a velocity which is so much that the trailing end of the fibers which are hanging and then swirling, they will develop so much tension that the fiber will actually move out from the main body of the bundle. So, there will be so much tension acting this way now because of very high speed, that even though the leading end of the fiber is buried inside the yarn, this fiber will be pulled out gradually, and if it is pulled out, then it is going to be finally lost. So, every wrapper fibers has a chance to get lost. All depends upon how much of the leading end of the fiber is buried inside the main bundle of fibers that we call yarn tail. See, yarn is already there here. This is the tail part of the yarn. See, the yarn which is moving through it, the tail is existing near the spindle tip, and the free flow of fibers which is coming is joining the tail part of the yarn. So, tail part of the yarn is basically wrapped part of the yarn, where the fiber wrapping is there, and there is a flow of fibers which is coming from the front roller nip and joining this yarn tail. So, within the yarn tail, part of the fibers are buried. Which fibers? Fibers which are actually swirling. Fibers which are not swirling, they are a part of the main body. So, they are nothing, they are not rotating at all. So, the angular velocity basically means, critical velocity means that this is rotating at such a omega, the centrifugal force is so much, tension is such that this tension will be good enough to pull the fibers out. So, all depends upon the value of omega and what is the length from here to there of this fiber which is hanging. This length L is going to be more if the distance is long. That is what it is being, we are trying to, I try to emphasize on it. So, therefore, the leading ends of the fibers will be more easily pulled out from the yarn tail, which results in ultimately these fibers will be lost. So, it will be fiber loss, and the fibers are lost, number of fibers in the cross sections are reducing, it will lead to thin place generation. That will be the net effect of it. And increasing long regular wrapping is also possible. Those who are going to wrap finally, suppose some fibers, every fiber is not going to be lost, some of them may not be lost. So, a longer length of the fiber will be available for wrapping, a shorter length goes inside the main bundle or within the core, the rest of the length is available for wrapping. That is what it is saying, that long regular wraps will be formed, that possibility is there, and decrease in tight regular wrappings and unwrapped sections. These are the various possibilities which are there, which have been observed by the researchers. So, resultant yarns becomes more hairy and a reduction in yarn tenacity at very high nozzle distance. So, very high nozzle distance may actually deteriorate the quality of the yarn. So, there is a shorter distance, there is a longer distance. So, we have to see that there are certain influences, some of these influences are positive in nature, some of them are negative in nature, and therefore, there has to be an optimum distance between these two, which one has to find out when somebody is taking, by taking some trials. Now, we come to yarn count. We can make a finer yarn, we can make a coarser yarn. The count range I have already said, it can vary between 15 to 65 NE, that is the range in which the yarns are spun. Tenacity mainly depends upon this, the ratio of wrapper fibers and core fibers. Let us see, in the cross section of fibers, you can say you can categorize them into two groups. One, some fibers which are wrapping, and the others are basically a part of the core. It is something like this. So, how many fibers are forming the wraps? The more the wraps, the more compression will be developed on the core fibers, and therefore, the core fibers will be able to resist the load, because more frictional resistance will develop. These wrapper fibers are actually developing radial pressure when the yarn is pulled. We want to break the yarn. Now, this pressure that develops because of the wrapping. So, how many fibers are wrapping, that will decide what is the magnitude of this force and how much strain we have imposed on the yarn. The other thing is, if I use more fibers, make more fibers to wrap, the number of fibers in the core, this is the core, will go down. It will be less and less. So, that has to be again here also that has to be an optimum. So, besides it also depends on the nature of wrapping, whether these wrappings are tight or loose or irregular, what it is. That means, length, tightness, length of unwrapped zone of the yarn. Say the yarn, if this part is wrapped, then this part is wrapped, and again this part is wrapped, like that. So, what is this zone which is not wrapped? If this zone length is longer than the fiber length, then if I pull the yarn, it will easily slip from here. Suppose A and B. AB, if it is long, then possibility of fiber slipping is going to be more when the yarn is going to rupture, because there these fibers are not experiencing much radial force. So, they can break easily, the yarn can break easily. So, that's why the length of the unwrapped zone is also important, that is this zone, and the mass irregularity of the yarn, unevenness of the yarn, besides the thin places in the yarn, all of them will have influence on the tenacity of the yarn, other than this ratio. With finer yarn count, tenacity has been shown to reduce due to higher wrapper to core fiber ratio, which reduces the number of load bearing core fibers and increase in unevenness and imperfections. So, going towards the finer count side means the tenacity, if I choose the same fiber and then keep producing finer counts, we will find tenacity to reduce. The fiber remains same, tenacity will reduce because of the reasons given here. One is this, and the second one is increase in unevenness and imperfections, and increase in wrapper to core fiber ratio. So, wrapper fibers becomes more in comparison to the core fibers. If the core fibers becomes less, then obviously load bearing fibers will be less. That will also reduce the tenacity. Now, we will just go to just the properties in general, not in details. Typically, we can expect the yarn to have low hairiness. The reason is simple, because wraps are there, wrappings are there. So, most of the projecting hairy ends will be forced to be on the surface of the yarn. They will be under the wraps. So, they will not be able to project out. Bulky, it will be bulkier and stiffer than ring spun yarn due to untwisted core fibers. That is why the yarn is going to be, diameter of the yarn a little bit more than the ring yarn, but it will be stiffer because of the wraps, tight wraps are there. Like rotor spun yarn also is stiffer because of the rapier fibers, such tight wraps which are there. Loose wraps will not make the yarn stiff. It is the tight wraps which are going to make the yarn stiff. So, if wrapper fibers increase means if more loose fibers are there, loose wrappers are there, the yarn may not be stiff. But if more tight wraps are there, then yarn will be stiffer. That means flexural rigidity is going to increase. Here stiffness is basically with respect to flexural rigidity, and this is also true in the case of tensile, also the initial modulus. Evenness, vortex spun yarns are worse than the conventional and compact ring span yarns in terms of yarn evenness. So, conventional ring span yarn and compact span yarns are much evener than this vortex span yarn. Tensile property, tenacity of vortex span yarns is 85% the tenacity of ring span yarns. So, compared to ring span yarn, they are little weaker. Tenacity of vortex span yarns is greater than the tenacity of air jet span yarn due to higher number of wrapper fibers. If we compare between air jet and vortex, then vortex span yarns are stronger. Breaking elongations are lower than conventional and compact ring span yarns, but higher than open span yarn. That has been seen. That is, breaking elongation wise, it is lower than conventional and compact ring span yarn, because most of the core fibers are actually straight and parallel. They are not following a helical path like in ring yarn is there. No, fibers are following helical path, so they can extend when we are trying to stretch the yarn. The fibers are perfectly straight and parallel. The fiber will stretch. There is no the spiraling of the core fibers is not there. So, they will not really extend much. That is why breaking elongation is less. With that, we come to the end of our slide. So, few effects of few parameters we have discussed. There are still a lot of research is going on the vortex span yarns, and there are still scope for doing research, because there are a lot of contradictions in the findings of the researchers. So, whatever, and because maybe that many things have not been studied in details. So, those who are interested to pursue some research in the vortex spinning, there is still a lot of scope to do that. Not many articles have been published, and there is still some scope still left. And in some of the articles we find that there is a some kind of, you can say, the contradictions in the findings of the researchers and the conclusion drawn out of those observations that have been made by the researchers. With this, we close this session. Thank you.